1.2 is solutions and initial value problems. Let's take a look at that. We want to talk about the concept of explicit versus implicit solutions to ODEs. So first, let's just take a look at the general form. So what's considered the form of a differential equation. So this is the general form of an nth order, right? That's the derivative, ODE. So that's pretty much what we'll be looking at. With respect to x, right? That's your independent variable, and then y is your dependent variable. So we have these different forms to look at. We call it capital F, and it's in terms of x, y, or you could say basically like x of t. And then you have your derivatives, dy dx, etc., all the way down to d n y dx squared. Okay, and then that's, you can say, set equal to 0. That's one form. So that would be the Leibniz form. Another way of writing that, and this is actually much nicer form, is x, y, and then you would have y prime, etc., all the way to y, and then the nth derivative equal to 0. So that's equation 1. And then often you can solve for the highest power, and that's used a lot for other things, theory and stuff. So equation, not squared, y and then n, that would be f, I don't know why they use a little f, but f x, usually they reserve capital F for the implicit form of the differential equation. But let's not get confused, the explicit form for the solution and implicit form for the solution of the differential equation. I don't want to get confused on that. Anyway, the rest of it's the same, and then it's in -1 is the power of the derivative. Okay, that's equation 2. So we have explicit form. So explicit solution. And this is the definition of the explicit form, definition 1. So a function phi of x, so it's like y equals phi of x. Then I don't know why they use phi, but that's what they use here. When substituted, or that when substituted, for y in equation 1 or 2, so either of those above, satisfies the equation for all x. So it makes it true, basically. So satisfies the equation for all x in an interval. Okay, so that's the explicit solution. And examples will help a lot with what we're talking about here. All right, so then next is the implicit solution. And frankly, that's more of what's easier to find. Sometimes it's impossible to find the explicit solution, but you can find it implicitly. So it's a relation. Basically, we're going to say implicit solution definition 2, a relation g of x, y, g of xy equal to 0 is an implicit solution to equation 1 on the interval I if it defines one or more explicit solution on I. So, like, what is that saying? So it's kind of you got to go through an example of what that's really saying. But that's what the definitions are. I wanted to lay those out, which I usually do. And we'll look at examples and see which examples are explicit or implicit solutions to the differential equation. So that's a little bit of theory and format, but we really want to, and we'll really want to jump into some examples to go over this. But then when we do problem sessions, we'll just basically be solving problems, which should help. So let's jump to some exercises in the book, and let's just take a look at number 4. Number 4 said the directions are determine whether the given function is a solution to the given differential equation. So basically, it's giving us both. It's not like you're having to find it. This is, again, this is kind of warm-up stuff to get a feel for what's going on. So if you're given x equal to 2 cosine t minus 3 sine t, okay, so that's the give. Is that a solution to this differential equation? Y double prime plus x equal to 0. All right, so how would you check to see if this, which is in what form do you think this is? That's explicit form because you have x, so x is a function of t directly. So this is clearly an explicit form of the solution. So that's your phi, but it's really just x. Phi is just a generic way of writing it. So if you basically then do what? So if you take this derivative twice, plug it here, and then take this function and substitute here, simplify, do you get 0? That's the question. So that's what you do to check this. Now, in reality, there's going to be multiple solutions to that form, depending on initial conditions and stuff. So, oops, I didn't mean to erase that. I was going to leave that like that. So that's the question. Let's check it. Okay, so and a couple more things. What's the order? Just for discussion purposes, the order is 2. It doesn't really matter if it's linear or not. I mean, you're just going to check it basically, and that happens to be, that is linear, right? So your independent variable is t, your dependent is x. So you have the x double prime and x. So that does make up a linear diffie-q. All right, so let's go ahead and take those derivatives. So this is a good point to pause and go ahead and do that ahead of time. So you get y prime equal 2, and then we just take the derivative twice, negative 2 sine t minus 3 cosine t, and then take it again. X double prime is negative 2 cosine t plus 3 sine t. Now to check it, you're going to substitute. You're going to substitute into y double prime plus x equal to 0 and see if that works. Sometimes I'll go sideways like this more than I would normally just to keep it all on one page for us. So when I substitute, I take all of this here that's my double prime, and then I'm going to add it to the given function, which was this. And normally you write it all out, but since I can do this, it kind of helps just to show you. So that's what I'm substituting in. And let's see, you have negative 2 cosine t, 2 cosine t, you have 3 sine t, negative 3 sine t, and that sum we can see easily that it's 0. Okay, so that's true. So you get a true statement, and that is actually true, we can say, for all t in the reals. So you want to, that's kind of one of the things we'll keep track of is for what values of the function is the statement true. Okay, not too bad, right? So far so good. Okay, let's do another one. Let's look at example 10. This is number 10. So same directions, y equal to, y minus natural log of y equal to x squared plus 1. All right, so is that, so if that's a solution to this differential equation, so this is dy dx equal to 2x y over y minus 1. So this is the idea. If this is a solution to this differential equation, is this implicit or explicit? In other words, okay, so here's your variable. That's your dependent variables y. Independent is x, right? That's what tells you. Do you have y isolated as a function of x? And the answer is no. So this is implicit. So implicitly, can you solve that? Or is it a solution that you can substitute into here and get a true statement? So that's what we're checking. Oh, so now I was going to go back one more thing. Almost forgot. Back here, what we would say then is, remember when we talked about phi? So phi of x in this case is the explicit solution. So phi of x, which is the 2, phi of t, sorry, phi of t. So phi of t, that's our independent variable, 2 cosine t minus 3 sine t is an explicit solution to that differential equation. Okay, so that's what we just talked about. Just wanted to have that down for you. Okay, so what we want to do next is to check this. We want to differentiate both sides implicitly with respect to x. So this is, remember doing implicit differentiation? I don't know, when we did it in Calc 1 and 3, I believe. So single variable and multiple variable, you do differentiation implicitly. And so when you do that with respect to x, you got to go through, and every time you see y, you just say y prime afterwards. And then after you take the derivative, and if you see x, you just take the derivative. That's the simplified version of that conversation. So you get y prime minus, and then the derivative of ln y is 1 over y. Then you got to say times y prime equal to 2, and then take this derivative, 2x, and I'll just say plus 0 to remind you. Okay, so then from here, solve for y prime, because we can see here that this is actually solved for y prime. So factor out y prime, 1 minus 1 over y equal to 2x. So y prime is equal to 2x divided by 1 minus 1 over y. And then that's a complex fraction, so you rationalize that, multiply by y over y, you get 2xy over y minus 1. And so we actually showed it directly that y prime is this right here. And so yes, it is a solution. We didn't have to substitute and check directly. We were able to solve directly for y prime. But keep in mind, the solution, this is implicit, right? So just a little note that this, that's what we call an implicit form of the solution. So we got a few more things to do, a little more conceptual concepts. And that's what's called the implicit function theorem. We'll talk about that a little bit. So there's a theorem that's not, you don't look at it unless you're a math major, basically. And it's called the implicit function theorem that guarantees the existence of that type of solution. That solution is going to exist, and it can be done implicitly. We definitely won't look at the proof of that. I have references if you want to see them. But it's done at an advanced calculus level or analysis level. All right, so we'll do that next. We'll go ahead and do another video and look at the implicit function theorem and another example. And then then we'll get into the initial value problem, and we'll do at least one of those.